Hello, hello. There's Lear. There's Vicky. There's a
Good
problem.
afternoon, Professor.
Good afternoon, sir. Good
Good
afternoon.
afternoon, Professor.
Oh, good afternoon. Wait, who was that? Wait a minute. Good afternoon, Lear, first of all. But good afternoon. Who was that? That wasn't Vicky. Who was that? That just, do you mind?
That was me,
Oh,
Fabia.
Amia. Oh, there. Okay, the green star. Okay, good to see you. Thank you. Thank you for using your voice. All right, awesome. I mean, good to hear you. Yes. Okay, and good afternoon, Aminata, and good afternoon, Vicky, and good afternoon, Gabriel. And chat now. Hold on. Sorry. It just goes to show you, like, while you're in class, the most fun part for me is the hellos. And but the one when you're watching the videos, the least fun part is the hellos. Am I right? Okay. But just goes to show you life is to be lived forwards and understood backwards, or the reverse. So good afternoon, Raina. Good afternoon for the double Vicky. Good afternoon for the double Gabriel. Good afternoon, Roger, who was here very early. Thank you. Good afternoon, Abid. Good afternoon. Hello, Melanie. Good afternoon, Caitlin. Good afternoon, Joel. Good afternoon, Keon. Good afternoon, Victoria. Wait, there's someone in the Okay. Uh, good afternoon, Aminata for the double. Good afternoon, Sonam. Hello, Yedaya. Yes. Okay. And hello, Anthony. All right. Awesome. Awesome. Oh, la, 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 la. Good. Okay. Good afternoon, Bridget. Thank you. Awesome. Oh, and Bridget, oh, for the double, Bridget. Oh, yes. Wow. Okay. Um, Sometimes I do feel like I'm teaching
Good
on.
afternoon, Professor.
Good afternoon, Mohammed, for the thank you. Uh, yeah, looking at these things, sometimes I do feel like I'm teaching on a farm. But okay, that's cool. I mean, who says barnyard animals don't need to learn physics? Nobody says that because why would they? All right. What I want to do today. Oh, I want to ask you a question first of all. Have you? I, yes. Have you done in lab? Did you do a board meeting about the Doppler effect in lab? I think it would. Yeah, that's my question. No. Okay. Good. Excuse me. Okay. Excuse me. Not yet. Oh, does that mean I see a no and I see a not yet? Is not yet you being polite to me? Like, do you know for a fact that you are going to, or you're just inferring that from the way I asked the question? Like, did your lab instructor say that you were going to, or okay, well, I'll assume. Okay. Um, so okay, either if you had already done one, then what we were about to do would be redundant, but you haven't, so it won't be redundant. So I want to spend one more day on the Doppler effect. Again, and I don't even remember this homework, the homework on the Doppler effect is very vaguely, it's a bad sheet. The sheet has to be redone at some point. But so it required a little bit more explanation. But I don't want you to be fooled. The reason we're spending like 3 days on the Doppler effect is, in my judgment, it is that important in physics in general. And it it just is that important. So I want to spend one more day on it. And then after this day today, we move to a totally different topic, kind of for the rest of the semester. Uh, Nothing is totally different, but it'll be a shift of focus for sure. But one more day on the Doppler effect. The ultimate goal of the Doppler effect, as I've mentioned, is that you should be able to analyze four standard cases of the Doppler effect. You should be able to use the same computational approach to predict the frequency as measured by the receiver for some wave that is sent by a source in a case. Let me back up and say this again. The Doppler effect is a situation where a source sends a wave to a receiver, and if either or both of the source or receiver has velocity relative to the wave's medium, any situation where either the source or the receiver is moving relative to the medium for that wave, then you have a Doppler effect, meaning if either the source or the receiver has velocity relative to the wave's medium, then the source and the receiver will get two different measurements for the wave's velocity. Like they won't agree on the wave's speed, and they'll both be correct, right? They'll get different measurements for the wave speed, and therefore they will therefore they will end up getting different measurements for the wave's frequency. I'm going to say that one more time because that's like the punchline. Like conceptually, that's the point. The Doppler effect is an effect wherein a wave source and a wave receiver measure two different frequencies for the same wave. I mean, that is what the Doppler effect is. So if it's a sound wave, the source and the receiver hear two different notes. Like that's literally what the Doppler effect is. Why does it ever happen? It happens if and only if the source or the receiver has some non-zero velocity relative to the wave's medium, right? So in common parlance, I'm just summarizing again, just because it is this important, and maybe I'll even get a chance today to tell you like one of the three or four big reasons for why it's so central to physics, in my judgment. Maybe I will, but for the moment, just bear with me, and hopefully, even if you think you get it or you've been doing it, like please make sure that you see the headline, the big picture. The big picture is when you're standing around in New York City and you hear like that, right? Like the motorcycle coming toward you and then going away, and you hear like, yes, that's the Doppler effect. Totally, that's the Doppler effect. But let's break it down for a minute. I mean, it's a very common thing, right? We experience it all the time. It's very real. It's not a theoretical, right? I mean, and honestly, that's one of the reasons I like this so much because it's like really real. But it has deep theoretical implications. But when you hear on the, sorry, I'm also going to change the view on the screen. Sorry. Hold on a second, and then we'll get rolling. When you hear on the street, let's talk about what is going on there. I mean, we're doing all the math. All the math that we've been doing for the last 2 days is the math of that. But what is that? First of all, let's please understand. Like when you hear, I'm assuming a motorcycle or I'm assuming a car or whatever. Like I'm not talking about a siren. I mean, it can apply to a siren, but of course, sirens already are going like that's already more than one note that's coming out of the siren to begin with. So that's that just makes it more complicated and more confusing. I'm saying even if there's a motorcycle or a car that's just hitting its horn, right? Just playing one note. Like, so to the motorcycle, they hear, right? Like that's an example. But like when that's happening, when there's a motorcycle going down the road, or even their engine's making that some kind of noise, right? So if they're going down the road and they hear, what I'm now arguing is, okay, they hear, in other words, their ear is measuring the frequency of some sound wave. Now, if they're coming toward you while that's happening, what we're arguing with all the math here and everything, we're arguing that if they're coming toward you while they're making that sound, that is one of the four cases of the Doppler effect. I don't care what the numbers of the cases are, but that would be if they're coming toward you, I would call that source approach, right? The source of the sound is approaching the receiver. You're the receiver in that case, right? So when they're coming toward you, they're hearing but they have velocity relative to you. Excuse me. I mean, that's true, but that's not what I mean to say. They have velocity relative to the air. The air is the medium through which the sound is traveling. The sound has a speed that is fixed, constant, and knowable relative to that air. So the sound comes out of the motorcycle going 340 meters per second relative to the air. Like everybody agrees with that, that relative to the air, the sound is going 340 meters per second, right? But they're also going at some speed relative to the air. They're going whatever, 40 meters per second relative to the air, right? So the sound is not going 340 meters per second relative to them. That's like super important. I mean, that's Galileo's principle of relativity. If they're coming toward you while the sound is coming out of them, then like every second, the sound goes 340 meters forward in the air, but they move forward 40 meters in the air. So to them, the sound is only 300 meters away from them every second, right? Like literally, the speed of the sound relative to them is 300 meters per second, not 340. And let's get it straight. That's not an illusion, and they're not wrong. Like that is literally, and it doesn't contradict anything. The speed of sound to them in their frame of reference is 300 meters per second. And their frame of reference is as valid as any other unaccelerated frame of reference in physics, right? Like really, 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 really. If you think that's not, if you think I'm sort of playing games like, well, all right, they think it's 300, like it's not, if you think, I'm not saying you do, but if you're taking away from what I'm saying, like, all right, the motorcycle guy, like, has this perception that it's 300 meters, but it's like it's his perception or it's her perception. That's not like really reality. We all know that the real reality is 340. Oh no, au contraire, mon frere. If you think that's just a perception, it's not reality, then how are we walking around on earth all the time feeling completely stable in our daily lives? Like every day we treat reality like there's a ground beneath our feet, while part of our brain says that that ground is going past the sun at 65,000 miles an hour all the time, right? It's because there isn't one objective velocity reality. Velocity is a relation between two objects, right? Otherwise, you would never get on an airplane. You know what I'm saying, right? Like, I think you know what I'm saying. So to that guy, to that motorcycle gal, the velocity of the sound is 300, not 340 in this example I'm making. So, but to you, you're standing in the air on the New York City street. You're standing in the air. So to you, the sound is going 340. Now you're both correct. You're both correct in your frame of reference. But now here's the, so you both, since one of you has velocity relative to the medium and the other one of you does not, then you guys disagree. You measure two different velocities for this sound wave. Now that itself could just be an abstract physics theory kind of thing to say that you could say, fine, it's true, but what do I care? But then we're saying, but wait, if you're disagreeing on the velocities, but you have to agree on the wavelength of the wave. Like that's what it's saying right here on the board. Like wavelength of wave relative to source has to equal. In fact, I'm even going to go like, well, that's a little, I'm going to go like that. Like it, thank you. It has to equal the wavelength of the wave relative to the receiver. Like once those sound waves come out of that motorcycle, and if each clump of air molecules is like for example, 0.77 meters away from the next one, I don't care how fast that motorcycle is going or how fast you're not going or whatever. If you guys were to look at the air molecules, the pressure pockets in the air, they're separated by whatever amount they're separated, 0.77 meters, let's say. And they're traveling in this wave toward you. Like the whole idea of wavelength is it's a gap between crests. That gap is not changing or subject to disagreement. While the gap travels from the constant flow of gaps travel from the motorcycle to your ear, right? If the air molecules are 0.77 meters away, according to the motorcycle, then they're 0.77 meters away, according to you. So you all agree on the wavelength. But if you disagree on the velocity, then you're going to disagree on the frequency because, just to remind you, I guess I'll put right here, because for any wave, velocity of the wave relative to whatever Sorry. Here, let me do this more clearly. Hold on. I'm saying that I don't care who you are. I don't care who you are. You agree on the wavelength of a wave. I don't care how fast you're going. You agree on the wavelength of the wave, but also you also agree on this. Like the velocity of a wave is the wavelength of the wave times the frequency of the wave in in any and every frame of reference. Like not like you have to be consistent. You have to just stick in one frame of reference at a time when you do the calculation. But velocity is wavelength times frequency, which is really just to say it's distance over time. Um, but so whether it's the medium looking at it or the source looking at it or the receiver looking at it, velocity is wavelength times frequency. So if you and the receiver both agree on wavelength, but you disagree on velocity, you have to disagree on frequency. So when the motorcycle is coming toward you, from its perspective, and it's going toward you. So each one of those air pressure pockets is going to be, say, zero point 0.7. I'm just assuming that this is like note A, like 440 on a 440 hertz. Then each one of the pressure pockets is going to be 0.77 meters away from the next pressure pocket. They're traveling along, um, or whatever the number is. They're traveling along, and they're going to start hitting your ear more frequently than they would have had the motorcycle not been coming toward you. If the motorcycle were just sitting still, they would hit your ear only so often. But since the motorcycle is pushing forward, it's bringing those pressure pockets together and they're going to hit your ear more often than they otherwise would have. So you won't hear a 440 hertz or whatever it might be. You'll hear something higher, like a 500 hertz. So you won't hear a middle A, you'll hear an A sharp or whatever. So when the motorcycle's coming toward you, you hear now now that, but you just hear that. You just hear First of all, I'm not saying it's getting higher and higher or anything like that. This is velocity dependent. Please write this down. I mean, what I'm trying to say with the motorcycle example, I'm trying to just bring this to real life and show you how this plays out as an actual thing. Comment 1 on the motorcycle example. Notice we are not talking about volume. This has nothing to do with volume. Yes, the motorcycle sound might be getting louder and louder as the motorcycle gets closer and closer to you, but that is a totally different issue. That is not the Doppler effect. That would happen no matter what. So first of all, if you're taking notes, please, comment 1 is the Doppler effect has nothing to do with volume, has nothing to do with volume. Comment 2, the Doppler effect has nothing to do with position. It has nothing to do with where the motorcycle is. It has everything to do with what its velocity is relative to the air and what your velocity is relative to the air. So comment 1 is this has nothing to do with volume. Comment 2, the Doppler effect has nothing to do with position. It's not volume, it's frequency, and it's not position, it's velocity. So the motorcycle is coming to you going, it's going it hears, and to you, you hear, right? Now you don't hear what the motorcycle hears, you just hear what you're hearing. So you just hear this, right? And maybe it's getting louder, but that's whatever. But you just hear this constant tone that's very high. But then the motorcycle passes you. Now it's going away from you. So the Doppler effect happens in effect in the other direction. Now the thing is going away from you. So the whole time, the motorcycle continues to hear the same tone the whole time. It's not experiencing, it's the one making the sound. It's not experiencing a Doppler effect. It's not experiencing anything unusual. It doesn't matter how fast that thing is going. It just hears the middle A. But now that it's past you, it's another different case of the Doppler effect. It's source recede rather than source approach. So now it's like you running away from waves at Coney Island or whatever. Like the waves are going to hit you less often, not more often. So now you'll hear a lower tone than what the motorcycle is hearing, right? So the Doppler effect is that while it was coming toward you, you heard a high, if you made this on a graph, it would be a high, like horizontal line. Then the motorcycle passes you, and then it's a low horizontal line, maybe say lower than the x-axis. And the x-axis, so you have two lines like equidistant from the x-axis that drop as from one to the other as soon as the motorcycle passes you. And the x-axis is what the motorcycle's hearing, if that makes sense. So you hear, do you see what I'm saying? Like, again, I'm just trying to reinforce, but I'm trying to say that the math that we're going to go back to, position. Right. But I'm saying it's not about position. So someone just put in the chat. I mean, I'm glad you put something in the chat. Put the word position, just as long as we're on the same page. I'm saying that the Doppler effect, none of the equations or the phenomenon of the Doppler effect are depending on position. They're depending on velocity. Does that make, hopefully that makes sense. Is that what you're reinforcing in the chat? Or maybe let me know, but I'll just go on. Bottom line, I'm saying, that common experience that you have, that is the Doppler effect. What that is going from one case of the Doppler effect, source approach, to a different case of the Doppler effect, source recede. And if a motorcycle were just parked on the street and just going, and just like blaring its horn, you would experience the same Doppler effect if you ran past the motorcycle, as long as, like literally, if you ran past the motorcycle, you'd experience that same thing, but you'd have to run fast enough for it to make an appreciable difference. Like, and the faster any object goes relative to the medium, the more dramatic the numbers are. Okay, so that's my summary of what we're talking about here. Okay, I hesitate to say this, but I'm going to turn it to you in a minute to do another. Remember, the whole homework and the thing that you're responsible for on one exam or another is that you need to be able to do all four cases, and you need to be able to do all four cases the same way, but get potentially different answers. So let me reinforce two. So I'm going to turn it back to you in a second to show me right in real time. You're going to do another case, and we're going to talk about it. Even though I know it was homework, or I don't remember when it was due, you can redo the homework accordingly. You can get all the points. Like I haven't even given the points yet for it. So hopefully this like helps those of you who are still struggling with the homework. But either way, I need to get all these answers. So I'm going to turn it to you in a minute. Let me say two more things. I keep saying over and over that you're responsible for being able to do each one of the cases this on your own the same way, but get different answers. The same way is the way we're doing it in class. Just as like a friendly, gentle warning, whether this applies to the midterm or to the final exam, friendly, gentle warning. I know there's a Doppler equation all over the web, like an equation for predicting the received frequency in any Doppler effect problem. Let me back up for again. Let me back up one more second. No matter what Doppler effect problem you're ever doing, hopefully it's becoming clear to many of you that the issue always is that you're given a bunch of numbers, and you're given what the frequency is measured by the source, and what you're trying to compute or predict is the frequency as measured by the receiver. That's always the goal of the Doppler effect is, okay, the source heard one note. What does the receiver hear? And again, they're both correct. I know there's an equation all over the web and in books that does this in like supposedly in one step for you. I am telling you now that equation is, it's not wrong. I mean, it's right. I understand it. And yes, it's a shortcut and all that, but it's far more deceptive than it looks. It's far harder to use than it looks. It involves far more memorization of than it looks. And I am telling, I don't usually say it, but as a gentle warning, when I ask you to do these Doppler effect problems, I'm asking in this case, I'm asking you to do them my way. If on an exam or something, you just use that equation that's on the web, I will demand that you break down the equation and justify it in terms of the principles of this class. Like, it's not that it's wrong. If you can fully explain why it's true and you can show how it comes from these fundamental principles of V equals lambda F and VAB plus VBC equals VAC, like, okay, then if you can, then you can, but you have to in order to use it. So I want you to see, I think it's much easier to just use the principles themselves. In other words, I'm heavily discouraging the use of that equation from the web. And usually, if I say it enough times in the class, anybody who does use that equation from the web that will never appear in your notes or in these PDFs or in these videos, the equation that's all over the web that has a plus or minus sign in the numerator and has a plus or minus sign in the denominator, it's one of those things where if it appears a lot in your exam, it's kind of an indication that you kind of are not using this class in order to do whatever. You get what I'm saying? Like it's a red flag. Don't use that equation. Not because it's, but you can. I mean, it's physics, but then you have to fully break it down and show exactly why it's true and how it works, which I think you, at that point, you might as well just be logical and do it this way. Um, Okay, that's enough on that. So don't use that equation. That's number one. Because it doesn't teach you anything. It doesn't show at all conceptually what's going on. But number two now, I'm going to turn it to you guys. Um, just as another teaser as to why we're spending so much time on the Doppler effect. A little teaser. I mean, like there's many reasons, but one little reason is the Doppler effect is most commonly experienced in daily life in the case of sound. And that's how we're analyzing it here, like Doppler effect for sound waves. But as I keep saying, the Doppler effect occurs when some source sends some wave to some receiver, and when either the source or the receiver has velocity relative to the medium for that wave. Well, it turns out that starlight seems to undergo a Doppler effect as it comes from stars to, I mean, this, you don't have to, I'm just saying this. The light that comes from stars, from distant galaxies to our planet, as of the 20th century, we have, spectroscopy and we have advanced techniques for coming to realize that when it comes to light waves, if there are such a thing, the frequency of a light wave is registered by the human brain as color, right? Just like the frequency of a sound wave is registered as pitch or note, the frequency of a light wave is interpreted as color. Well, it turns out that starlight, when it leaves stars and comes to us, we measure slightly different, but measurably different frequencies, colors of that light from what we have independent reason to believe the stars or the star frame of reference would measure. So, in other words, as of mid to third quarter 20th century, astronomical evidence continues to suggest, more than suggest, like confirm, starlight undergoes a Doppler effect. We experience a different frequency of starlight than what stars experience. And that's why we believe that stars are moving well, and I'll just add one more. What we in general find is that the frequencies of starlights that we measure in the frame reference of Earth are lower frequencies than the frequencies that would be measured in the star frame of reference. And we know that from chemical breakdowns of spectroscopy. I mean, long story there, but we know that independently. So we have the evidence keeps mounting and mounting and mounting as of the mid 20th century, leading us to have no choice. But assuming that light sometimes does behave like a wave, we'll get to that. Assuming that light can behave like a wave, not assuming, but coming to believe that light can act like a wave, and coming to believe that the frequencies of light waves are what we interpreted as color, and coming to believe that these light waves that come from stars, they undergo Doppler effects. We come to believe that in general, stars in general must all be receding away from us here on Earth. This is where we get the notion, the belief, the worldview of an expanding universe. The reason we believe that the universe, I'm serious about this. And I keep saying believe because, like obviously science evolves all the time and all that kind of stuff, right? I'm not, but don't get me wrong. Anytime I say the word belief, I mean, I believe the stuff that I'm teaching you. Like, I'm not saying that one belief in physics is any weaker than another, but to the extent that all of this is some kind of set of beliefs, or whatever you want to call it, all theories or all models or whatever. I'm saying just as much as I believe lambda WS equals lambda WR, I believe that stars in general are receding from the Earth because I believe that the light that's coming from stars undergoes a Doppler effect, that we generally measure frequencies for light waves that are lower than what the frequencies would be according to the star frame of reference, which we do know for independent reasons known as spectroscopy. So therefore, if the Doppler effect is correct, and if it applies not only to sound waves, but to waves in general, including light waves, then we have a huge amount of overwhelming evidence to suggest that stars are in general moving away out from us all the time. But we're not special. There's nothing about us that pushes stars away. So apparently, things all the time are moving outward in general, i.e., the universe is expanding. I.e., if you take that movie in your mind, if you believe that for a minute, just entertain, I mean, you hear it all the time. It's a very weird idea, but if you entertain it for a moment that the universe is expanding, and you think of that as a movie of the universe where you take a movie of the universe and it's getting bigger and bigger all the time, well then you run that movie backwards in your mind, and that would suggest, if you take it all the way back to the beginning, that the universe was really small, right? That's where we get the idea of the Big Bang from. We're interpolating or extrapolating backwards. Once you say the universe is in general, as the arrow of time moves forward, the universe expands. Once you believe that, then that means turn back the hands of time in your mind. And if originally the whole thing must have been really, really small and then exploded out. That's the notion of the Big Bang. Now, I'm not telling you what I'm saying. If you ever read about the Big Bang or expanding universe in the New York Times or whatever, like don't just accept it as like just, I mean, it's a crazy idea. It's a very counterintuitive idea. It's not something that you're not born believing that, I don't think. But it's not out of nowhere. It's not because we want to believe it. In fact, I would say that a lot of people don't want to believe it. But why they believe it is the Doppler effect. So that's just one example. That's one example of where the Doppler effect is like a very important way of looking at things. So that said, so that's just whatever, a teaser. I'm not saying you're going to have an exam on like the redshift of starlight, but that's just an example. Now, what I want you to do right now, and we have 40 minutes left. What I want you to do for real right now, um, and I'm going to put you in breakout rooms. I Yesterday we did a case of the Doppler effect. We did Yesterday we did the case where the source was approaching the receiver, and we did those numbers from the homework, like 340 meters per second for the velocity of the wave relative to the medium, 80 meters per second. I mean, 800 hertz for the frequency of the wave relative to the source, etc. Those numbers. I want you to use those same numbers again. I'm going to put you in breakout rooms in a second. I want you to use those same numbers again, but solve for the frequency according to the receiver in case, in a different case, in the case where the receiver approaches the source. Okay, now it's possible that that is the case we did last Monday together. I honestly cannot remember, and I think we did it super fast. So that's fine. If we did it Monday, you can turn back to your notes from there, and you can like copy that or slow them down. But I want you to practice. And I want you to do that case. Make sure, even if you're taking your notes from last Monday, because I know we did it super fast. So I want you to literally on the paper, like make sure that you're getting the numbers by the exact same method we did 2 days ago. Like you should be able to see side by side that you're literally doing the same steps, the same methods, only zeros are appearing in different places and 80s are appearing in different places or whatever. And so at the end of the day, you're going to get a different number. And I'm going to tell you again, I'm going to shut up in a second. You're going to do it. I'm going to put you in breakout rooms, right? Um, and I'll put the instructions in the okay, I'm going to put the instructions in the chat right now to make sure we're all clear on this. Hold on. Actually, no, I'll put them on the board. Hold on. Okay. So you're going to do receiver approach today. All the numbers you're taking from homework 4, it's the same numbers we used 2 days ago. You're going to, and when I say solve, I always mean when I say solve, I mean find the frequency of the wave relative to the receiver. That's what you're always looking for in a Doppler effect. So you're going to solve that in breakout rooms in a second for the case of the receiver approaching. But when you're done, I want you to compare to the source approaching, which is what we did 2 days ago. Like, first of all, make sure that you did the same method, see that you did it, and then look at the numbers that you get at the end. See if they're the same or different, and try to discuss in your breakout room, like why they are the same or different. In fact, well, uh, I'll even say, sorry, even before you do any calculations, I should have said this first. I apologize. Even before you do any calculations, once you're in a group, like ask yourself, like Monday, we did the Doppler effect of the of the source running into the receiver while it made the sound. Now I'm asking you today to do a case where the receiver is running in toward the source while it makes a sound. And remember, this whole thing is based on Galileo's principle of relativity. So I want you to predict before you even do anything. Like, how should this case compare to this case? Like, should we get literally the same result, or should this one be a higher result, or this one be a higher result, or what? And by result, again, I mean the frequency of the wave as measured by the receiver. It's going to be some number that is not 800, right? The frequency of the wave relative to the source is 800 hertz. You're solving for what different note is heard by the receiver. We got a number on Monday when the source is approaching at 80 meters per second. Now, today you're going to try to get a number for when the receiver's approaching. Do you think they should be the same number? Why or why not? Like, first predict, I'm saying, then do the calculations and compare your results. I'm going to put you in breakout rooms in a second, and I'll also pause the recording, of course. Well, not of course, but I will. But let me just ask you before I put you in breakout rooms, can you just raise your electronic, even if you're like, this is not a test. I mean, this is practice. Oh, we are going to get back together and discuss it, and I will go over it, but it's just practice. So you might get things wrong. That's fine. But is it clear what I'm asking you to do? Like raise your electronic hand if it's clear what I'm asking you to do. Awesome. All right, that was fast. Okay, 3 people, 4 people. Okay, only 5 people. Okay, 6, 7, 8. Okay. All right, so it's sort of clear. All right, cool. So I'm gonna make breakout rooms now. Thank you. Awesome. All right, so breakout rooms. Hang on. Create. Okay. And again, please do take advantage of your breakout room. Like work with the other people. You're ultimately you're trying to get an answer. You're trying to get FWR and you're trying to compare that. Well, you're first trying to predict. I'm sorry, predict it, then try to get an answer and then compare that answer to what we got on Monday. And I'm going to ask you to move somewhat quickly because we've now technically done this 2 cases already. We've sort of done this twice technically. So be prepared for me to call everybody back and sort of hear from each group one at a time. Okay. All right. So here comes okay. So, all right. So I have the rooms. Yeah. As soon as you see your room, just go to your room, please. And yeah. Oh, okay. Fair enough. Right. And just do what you can do. I hear you. If you can only contribute so much to your group, only contribute so much. But yeah, I hear you. If you're not, no one's feeling perfect. I'm not expecting perfection. I get it. Um, oh. Okay, so you're all back. All right, you're all back. Okay, so I might have cut you off. You may not be done. I realize that, but we have 15 minutes left, so I want to make sure we get some resolution on this. So first of all, I'm going to put you on the spot. I mean, I don't mean to put you on the spot, but like any, raise your electronic hand if your group got an answer. Oh, is that it? Raise your electronic hand. Oh, yes. Okay, okay. So, and keep them up. Raise your electronic hand if your group got an answer, i.e., got an FWR. Keep them up. Okay, put them down. Raise your electronic hand if your group did not get an answer. I'm just just see where we're at. Raise your hand if, okay. So some groups did and some groups didn't. Okay, okay. Fair enough. Okay. And then some groups didn't vote, which kills me, but okay. So then my goal, I want you to have an answer by the end. But very quickly then, any groups that got an answer, can I just quickly hear from a representative from any group that got an answer? Can you just like unmute and say the answer you got? Um,
988.2 hertz.
okay, 988.2 hertz. That's what, okay, awesome. Thank you. And I'll say this, that is higher than 800. So I like that. I'll also say that it's lower than 1048 or whatever it is that we got Monday. So that's noteworthy. Okay, that's one answer. I'm not saying right or wrong. Honestly, I don't even know. Any other group that got an answer? So far we have 948. Any other group that got an answer? Oh, was that the
We
only?
got the same.
You got the same. Okay, awesome. So the same. Any other group that got an answer? It, is it true that there are two groups that got an answer? Is that right? I mean, again, just tell me if you can I get a representative from a group that did not get an answer? Can you just honestly tell me like where you got stuck or how far you got, or if you just ran out of time, or if you got confused? Just give me a quick. This is not about shame. This is just about me knowing what to teach. Somebody who didn't get an answer, could you just give me a quick summary of like where you are? That is a rough
Um,
question.
our group, we made the prediction, right? It took like a little bit. We made like prediction that it would be higher for the receiver approach. And yeah, we are solving it, so I guess we ran out of time.
Okay, fair enough. That's fair. And you, oh, and good. And I should have asked. I always forget to. I'm glad you told me. So you made the prediction that the frequency as measured by the receiver would be higher than the answer we got on Monday. Which I will actually also, which is interesting. Okay. Uh, okay. Um, for what it's worth, the two groups that got the same, well, I guess, okay, last question. Both the groups that got the answer, can you just quickly tell me, because I should have asked, what did you predict?
That the frequency of the case that we just did would increase, would be higher than if the source was moving towards the receiver.
Okay, so same prediction as Sonam's group. Okay, good to know. Which, and also very honest, right? Because if I understand correctly, that's like not what you ended up finding, right? Like you got a number that's actually lower, I think, right?
Yes, it is lower.
Okay, thanks. I love the whole. Okay, and is that the same thing with? All right, we've got 10 minutes. Okay. What I'm going to quickly do in 10 minutes. Okay, I'm going to say first of all, and I'm going to turn on my board in a second. Well, all right, I'm going to do it my okay. I'm going to put on my board. Hold on one second. So I'm going to do it quickly because it sounds like there's a lot of groups that still would benefit from a complete solution. And I do appreciate that the two groups that got an answer got the same answer. That's a good sign that they're probably doing something right. That's good. But it is also noteworthy uh, how the finding compared to the prediction. I will tell, and I appreciate the honesty that they're saying basically they predicted one thing but got another. So there's something worth talking about here, no matter who we are, even if we got an answer. Apparently, it's different from our prediction. I will tell you. Okay. I will tell you right from the get-go, if I'm doing this case, if I'm doing any case, what I would have done, and be careful about this. I think it's important to recognize that what I would have predicted, I would have predicted. Sorry. I would have predicted. I want to make it clear that I as a physics person who's learning physics, I would have absolutely predicted. And every time I think about this roughly, I always think that whether the source is approaching or the source or the receiver is approaching, I would think that we would get the same Doppler effect. I would have thought that. And I want you to know that because I think that's because this whole thing is based on Galileo's principle of relativity. Whether you say that the Earth is moving toward the sun or the sun is moving toward the Earth comes to the same thing in the universe. That's the point of relativity, right? VAB equals negative VBA in relativity. So I would have thought that whether you're running toward the waves whether you're running toward the source of the waves or the source of the waves is running toward you, I would have thought, well, this is all about relativity. Who cares? If all the numbers are the same, I would have thought, who cares? And qualitatively, it's true that whether you're running to the receiver or the receiver is running toward you, but in both cases, the received frequency will be higher than the source frequency. Qualitatively, it's true that both approach cases get a high number. But apparently you guys are right to predict that they wouldn't be the same number. Now, I wouldn't have thought that, but apparently you're right. And I need to explain why. But let's do the numbers really quick. How do you do the numbers? You do sub-step, like this is all under step 4, right? But sub-step A, I solve for the wavelength of the wave according to the source. How do I do it? I do the velocity of the wave according to the source over the frequency of the wave according to the source. What's the velocity of the wave according to the source? It's VWM plus VMS. But what is VMS? If the receiver is moving, then VMS is 0, right? So the velocity, so the wavelength of the wave is 340. Sorry. That's supposed to be an F right there. Sorry. 340 over 800, which equals, I think we said yesterday, 0.325, right? That's step 1, or step A. Sub-step B is I say the wavelengths, everybody has to agree on the wavelengths. So then sub-step C, I go over to the receiver and I go, okay, well, I'll go to the next page. I go over to the receiver frame of reference and I say the frequency of the wave according to the receiver must be the velocity of the wave according to the receiver over the wavelength of the wave according to the receiver. What's the velocity of the wave? Now, and notice I'm doing the exact same thing. Like whenever I want to get a velocity, I always have to use Galileo's principle. I have to add two velocities together to get the one I'm looking for. Just some in one step, one of them is always 0, but which step you have a 0 depends on which case. So VWM plus VMR over wavelength. So, but what is VMR? Well, VMR, like, what's the velocity of the air relative to the receiver? It must be the opposite of the receiver relative to the air, right? And the receiver, according to the air, in this case, I should have drawn a diagram. The diagram is this. The diagram is that the receiver is going toward the source, right? But we always make the direction of the wave positive, right? We have 4 more minutes. So the velocity of the receiver relative to the air is negative 80 if the receiver is approaching, right? It's negative because it's going against the direction of the wave. So it's negative 80. So the velocity of the medium relative to the receiver is positive 80 meters per second. In other words, the air is coming toward the receiver in the same direction as the wave at 80 meters per second. Therefore, the frequency of the wave relative to the receiver is 340 plus 80 all over 0.325. In other words, 420 over 0.325, 420 meters per second over 0.325 meters equals, oh wait, there's something in the chat. Sorry, hold on 1 second. I'm doing 2 things in one. I'll get the chat in one. Unless you're about to tell me that I made a mistake somewhere, which we'll find out in a minute. Did I make a mistake? This is different from what you guys, hold on, I'll look in the chat because it looks like maybe I made a mistake. But let's see. What? I see what you're saying about your prediction. That's very why someone just said that they misunderstood their prediction. I'm very, all right, I don't want to get bogged down because we only have 2 minutes, but the person who just said that they misunderstood the prediction thing, I actually suspected that and that's very smart and honest of you to realize that. Yes, I think you did too, but very good that you realized that. So, but unless you guys think I made a mistake, I mean, we have 2 minutes left. I think. Oh no, but the wavelength is 0.425, right? Not is it point? Yes, I think you're right. I think you're right. Sorry, it's 0.425. You're absolutely right. Is that what you're saying? Yes, it's going too fast. You're absolutely right. Right. It's is it 0.425? I just misremembered it. We have 1 more minute. Is that yes, thank you. No, thank you. I was catching that just yes. So um we have 1 more minute. Okay, so now so I believe we get this. Stop me if you think not. I know we have not even 1 minute. I get this answer, which I think is what you two said. It is higher than 800, as it should be. It's less than the one from Monday, which some of you predicted and some of you didn't. Here's a bottom line with what, the bottom line is that this thing is different from the answer from Monday, even though or because relativity is driving this entire phenomenon. The reason it makes a difference, whether the source is moving or the receiver is moving, is because it's not, and I know it's 1:30. The important takeaway here, the reason you want to be able to do the one method and get 4 different answers rather than what I would have predicted to be 2 different answers, the reason is that what we're really showing here is that relativity is happening, but it's not about the relationship between the source and the receiver. It's about the relationship between the source and the medium versus the receiver and the medium. In other words, if this is my last thing, if relativity means that the laws of physics hold in every frame of reference equally, if the sun is as legitimate a frame of reference as the earth, what this is showing is that the medium for a wave is a legitimate and necessary frame of reference as well. The medium for the wave is a frame of reference, and things are being related to it, not to each other. And so a medium is central, vital to the motion of a wave and to the Doppler effect. That's the point. Okay, you've been very patient. It's 1:31. I will see you Monday. Thank you for your patience. Have a good day. Yes, and I'm going to stop the recording. Okay. Oh, yes, Vicky, question. Let me stop the record.